Welcome back, everybody, and here we are for Chapter 2. Chapter 2 is going to be Science, Matter, Energy, and Systems. You really got to fasten the seatbelts here. It's going to run fast. It's all material you should know. We're probably going to go a little deeper, but this is a very important chapter. It's going to come up over and over and over. We're going to have to do the things in this chapter throughout environmental science, throughout science period, basically. So let's go ahead and dive in and see what she holds. So first off, a case study. Make sure you pay attention to these case studies. Don't skip it because it's not the text, it is the text. These things get referenced on the AP exams all the time. You will see them in FRQs, or you need to be able to pull information, something that is specific, because you got to do details. So let's look at that first environmental study. They're conducting an experiment, a large part of what this chapter is about. You're going to design experiments for me throughout the year. You're going to have to be able to design an experiment for the test. But the good news is you should know how to do that. You've probably done it multiple times. And in reality, you actually do it all the time. You just don't think about it as an experiment. But let's take a look at the one they had. This was an experimental forest in New Hampshire. Scientists wanted to know, if we are cutting down trees, if we deforest an area, what does it actually do? Not just what we think, but let's get some measurements and find out for sure. So they took a experimental forest area, they dammed up a creek area and another. They tried to get same areas, same. One is the control group, and the other is the experimental group. So they dammed up one, that way they could measure the flow of water coming out of the dam, and they could then also go back, note how much water, nutrients that are in the ground, in the water, etc. Dammed them both. One winter, cut down the trees, and one just cut the trees and let them drop. They didn't haul them out. Sprayed to make sure new growth wouldn't come back quickly, and began their experiment over 3 years. So they had a control group, and they're comparing the experimental group, the cut down forest. And, picture back up here to take a look at it. But once again, the strip site had 30 to 40% more runoff. The vegetation helped control the runoff, absorbing the water so it stayed within the forest, but instead more water ran off. Faster water runoff led to soil erosion. The soil erosion also led to more dissolved nutrients. So we got a very specific idea of something that was happening from this experimental site. So here we are diving in. We're looking at this science, matter, energy, etc. First one is science. You have covered this probably each year of middle school. Every time you've taken a science, we've talked about nature of science to a degree, or the scientific method. And that's what we're talking about here. When we want to discover how nature works, which is by and large environmental science, humans' impact on the environment, the natural world, we have certain tools. Observations, simply looking. But remember, observations are not just looking. I open the refrigerator, ooh, something's gone bad. I smell things. I go up to touch the door and the doorknob's really hot, and I smell smoke. There's probably a fire on the other side. Observation is not only what we see, but all of our senses playing in. We take measurements. We measure things. Whenever possible in science, we like to quantify our data. 2 cups of water, 3,000 gallons of water. It was 92 degrees Fahrenheit, or it was 36 degrees Celsius. Quantify, we take measures, and then we do experimentation. We're going to try and find out what happens. These are our very basic tools. And to do that, we typically follow the scientific method. Now, you may have heard this as the scientific method. We may have talked about it as scientific inquiry, tools of science. It's really all the same thing. We do always tend to follow a method. Now, it's not linear as it normally gets approached. It's really more circular. We get to the end and we tend to go back and revise, run through it again until we feel fairly confident about our data. But anyway, those simple steps are: we identify a problem. It might start with a question, and the question or there might be a problem which leads to a question, but somehow you're going to have a question in there which is leading to a problem. We're going to gather relevant data. We're then going to propose a hypothesis, an explanation of what's going on. We will perform an experiment. Then we'll collect our data from the experiment, analyze that data against our hypothesis, modify the hypothesis as needed, go back through it again, analyze the data, and eventually draw conclusions. And lastly, we publish our results. A lot of times we'll do something like we develop a model. It might be a mathematical model to represent something that's going on. E equals mc squared. Energy equals mass times the speed of light squared to represent something in reality. And we'll use models often to study very complex systems like the climate. Many things going on. Low pressure, high pressure, season, tilt of the earth, many factors involved. So let me take you through this in simple. If you're ever curious, what are the steps of the scientific method, and you get lost, you don't have to really memorize them. Just think of this scenario. You got to get dressed. Now pick a special occasion. A wedding, a funeral. I'll pick first day of school. Because most of us first day of school don't just grab whatever's in the closet. People tend to fall into one of two groups. You want to stand out or you want to fit in. So you look in your closet and go, ooh, I'm going to get my nice new shirt that's going with my nice new skirt and my fancy new shoes. Well, you started off with your problem. What am I going to wear? And then you make your observations. You open your closet, you look in there, oh, these are my clothes. I can't wear something I don't have. So that's your observations. This is what I have. Then you begin to form a hypothesis. If I put this shirt on with these pants and those shoes and this belt, I will look nice. I will look sharp. I will blend in and not be noticed. It all depends on what your goal is. Your hypothesis is, if I wear this, then whatever. Then you conduct your experiment. You put the clothes on your body and you walk out of the house and you're conducting your experiment. While you're conducting your experiment, you're gathering data. Ooh, she said she really liked my skirt. He said I looked really sharp. That guy kept looking at me and couldn't look away. My teacher said, you look really nice today. You draw your conclusions. If I wear this outfit, I do look nice. Or, you know what? Nobody talked to me today at all. It was like I was invisible. This is the perfect outfit to not be noticed. I am a gray man. Nobody saw me. Whatever it is. And you publish your results. Now, here's the thing that comes down really between science and, as Adam West from Mythbusters would say, just screwing around. In science, we write it down. We would publish it. Now, this is where you take your picture of yourself in your selfie, you post it on your website, and you go, wow, I look fabulous in this. That's your posting. So in the getting dressed one, you may not do it. But let's say you're going to a wedding and you put this on and you walk outside and your mom goes, what are you doing? Are you crazy? We're going to a wedding. You have to be nice. Go put on your suit. Well, now you went outside, you conducted your hypothesis, you gathered data. This is not what you wear to a wedding. I need to go put on my black pants, my white shirt, whatever. You gather data and then you revise your hypothesis. I put the suit on, I walk back out, Mama goes, oh, you look so nice. And then we go off to the wedding. That's it. That is the scientific method. You do it all the time. You just don't think about it formally. If you ever get hung up, what's the next thing to do? Run through it. I have a question. What am I going to wear? I make observations. These are the clothes I have. I devise a hypothesis. If I put this, this, and this on, I will look sharp. You conduct the experiment. While you're conducting the experiment, you gather data. What are people saying about you? And at the end of the day, you draw a conclusion. It was good. It was bad. I couldn't really get good data, one or the other. Now, another thing we'll talk about really is scientific theory. And these are very well tested, widely accepted hypotheses, like climate change is a theory, the theory of evolution, the atomic theory. There's lots of theories. I've been experimented on many times. Many people have collaborated, and we feel that they point towards what is actually happening in the real world. We refer to those as theories. And we make advances through these. It's where our scientific knowledge base comes from. We gather this data, we dictate it, follow through. It's publishing those results that allow us to learn. If we don't publish, we don't learn anything. I stand on the shoulders of giants, people before me that learn things. I don't have to go back and work out everything about the theory of evolution. I don't have to work out the whole theory of the atom. I can learn from them and build on it today. And it's because of our publishing data that allows us to do that. And then new data and analyzing that data can lead to a revised hypothesis. We can refine it and get it a little better, a little better, a little better. One of the real important things in science is critical thinking. Critical thinking and creativity. They may not sound like they go together, but they really do. Scientists tend to be skeptical. You come up to me and say, "Oh, Mr. Pettit, if you take this little pill, you'll lose 10 pounds in a week." My first thought is, I don't think so. Let me look at the data. What's happened with other people? What does this pill actually do? What's going on? My first thought is to be skeptical. I want more data. I want to find out. This is the mind of a scientist. We're inherently skeptic. Not that we don't like things, we don't believe things. We want to know why. We want to get to the root of it. What's really going on? So we want to evaluate the evidence at hand. And I see, oh, okay, all these people have done it. They've lost weight. And I look at it and find out, oh, okay, it's actually some form of a stimulant to make me active, and it's an appetite suppressor. So I'm not going to eat, and I'm going to do a lot more exercise. All right, 10 pounds in a week might be a lot for me, but for somebody that's fairly overweight, okay, may have some merit to it. I want to evaluate the evidence and the hypothesis, and I'll look at as many reliable sources as I can. And I want to identify my own personal assumptions, biases, and beliefs. I need to try and remove them as much as possible. We all have biases. We all tend to think this or that thing or the other, and we need to be careful that we don't let them influence our thoughts when it comes to science. And that can be tricky, and especially before coming to a conclusion. We have to be willing to say, my hypothesis was wrong, and that is actually correct. It's important in science to be able to be disproven and accept that. Imagination and creativity, along with intuition, are also very vital. I just have a feeling it's going to be this. So we design an experiment to test it and find out. If there's no imagination, if there's no creativity, we don't learn as much. We're not all going to do it the exact same way. In this class, I'm going to have you design some experiments. Now, you're going to be limited with resources and time possibly, but it's going to be up to you to come up with a solution so that you can answer the question, because that's ultimately it. Science has a question. We design experiments to try and answer that question with data, and the data is where we draw our conclusions from. When we talk about in science, we talk about scientific theory and scientific law. There's not a difficult thing between these. I always do it very simply. A theory is a why and a law is a what. A scientific theory, well, something has been widely tested, theory of evolution, Big Bang theory, where it all came from. It's been widely tested, it's supported by evidence, and it's accepted by most scientists in a field. Not everybody. Not everybody's always going to agree with the same thing. We have our own assumptions and biases and things that we're looking at. But a theory is widely accepted by most scientists. That's a theory. It's a why. Why did this occur? Why did this happen? I can't say definitively in the theory of evolution where we came from. It's too far back. But I can look at the data and say this must be the case. Why? A scientific law is a what. What will happen? I pick up the mouse and I drop it, it will fall. Law of gravity. It's a what. What will happen next? It's not explaining why, it's just saying this will occur. We use scientific laws to design a lot of our experiments because we know if I do this, this will happen. That's a law and allows me to have knowledge going into something. A theory is a why, a law is a what. What will happen next? Widely accepted description of what happens repeatedly and the same way in nature. So, theory is a why, law is a what. Now, few other terms we've got to be able to understand and differentiate between. Reliable, unreliable, and tentative science. Now, it's not brought up here, but we could also talk about pseudoscience. Anyway, reliable science. If it is reliable, it is data-driven, strong hypothesis, there are models to back it up, theories behind it, and laws that are widely accepted by experts. This would be reliable science. So, yep, okay, you followed the scientific method, you did things properly, there's only one variable being tested at a time. This looks solid. Unreliable science. This is where results get presented as reliable, but however, they haven't been peer reviewed and nobody's really been looking at to discredit it. This isn't pseudoscience, it's just unreliable. Oftentimes I'll read in the news and it will say, certain study says protein doesn't really help towards building muscle mass. And I read the study and then eventually it'll say something like, further tests need to be done. This was done with 15 subjects and it's kind of trying to counter what reliable science is saying. It's unreliable. It was one experiment done in one study with a small group of people, and that is what that person found with that small group. But it's not reliable science yet. It hasn't been peer tested. Other people haven't repeated it, gotten the same results, so it's unreliable. You need to look for that when you're reading news articles, magazine articles. Not uncommon for them to just publish, ooh, this person found this. Is it reliable or is it unreliable science? And then there's tentative science. And this is also, you'll get in newspaper articles a lot. It's preliminary results, but there hasn't been adequate testing yet. You know, we're going, ooh, it looks like this might be the cure to cancer. No, it's tentative. Hasn't been adequately tested, hasn't come under peer review, it's not been in a wide enough audience, something of this nature. Now, pseudoscience is something that sounds real, but it cannot be disproved. I use the old thing like aliens live among us. Well, I can't disprove it. I say, well, you can't see one. I say, yeah, well, they're invisible, or they hide, or when people have an answer to everything, but it has to be disproven. I say, show me an alien. They say they're hidden. I can't disprove there are aliens among us. However, if I were to say there are no aliens amongst us, that can be disproved. You bring an alien up and I am automatically disproved. Science has to be able to be disproved. I need to be able to do an experiment that says, no, that's not it. Then we can revise our hypothesis and come up with something else. So reliable science, tested, true, been repeated. Unreliable science, things are being presented as reliable, but they have multiple variables, there's something not right. Tentative science, it might be being done right, however, there hasn't been adequate testing. Pseudoscience, completely different. It is not unprovable. Real science has to be, I have to be able to disprove it. It's a very important section. Now we have limitations. I say I have to be able to disprove it. Now we can disprove something, but I can't prove things in science. We have strong correlations. My hypotheses are supported. I can't prove Crest toothpaste gets my teeth whiter than Colgate, but I can set up experiments, gather data, and then draw conclusions. But I'm not proving. We lead to high probability. The higher the probability, the more likely something is true. Also, we're not free of bias about our own hypothesis. Whenever you're conducting your experiments, be very willing to say, my hypothesis was wrong. My hypothesis was not supported. Don't be too strongly influenced by your own bias. Be willing to adapt, change your mind in light of new information. Systems in the natural world often have very many variables and complex interactions. This is where mathematics and statistical models really help us. I'm grading tests. I'm curious how the class is doing. Ooh, this person made a 98. This person made a 92. This person made a 68. This person made a 43. This person made a 71. This person made an 81. And looking through it's too much data. I don't have a feel of how the class really did until I pull in statistics. I add them all up, divide it by how many people are in the class, and find out, oh, the class average was 82. Wow, we did really well. Sometimes it's hard to pull all the little tiny bits of data until we can use a mathematical model. Then it begins to make sense. And then also statistical tools are used when it comes to estimating very large numbers. Talk about population and population growth and etc. Statistics play a huge part, and we'll use them over and over in the world of science. All right, well, that's it for Chapter 2, Section 1, Science, basically nature of science. Take care, guys, and we'll see you next time.